So we've made it to the end of Unit 4. Here's Part 3 of Chapter 17, and this is where we make this subtle transition to talk about the normal model. So when dealing with a large number of trials in a binomial situation, making direct calculations of the probabilities used to be extremely tedious, or in fact impossible, and mathematicians would have to utilize this binomial theorem. So fortunately, the normal model came to the rescue. And actually, nowadays, this is kind of a moot point because it's the calculator that comes to the rescue. So for our purposes, we're going to showcase where the normal model comes in and the beautiful nature of its simplicity. So as long as this condition is met, the success-fail condition holds, we can use the normal model to approximate the binomial probabilities. So this condition states a binomial model is approximately normal if we expect at least 10 successes and 10 failures. So the way we write that is NP is greater than or equal to 10 and NQ is greater than or equal to 10. Remember, P is the success, Q is the fail probabilities. So when we use the normal model to approximate a binomial model, we are using a continuous random variable to approximate a discrete random variable. I know that sounds confusing, but continuous means I can be every value, and discrete means I can only be X number of values. So to correct for this, we must use a continuity correction factor. So when we use the normal model, we no longer calculate the probability that the random variable equals a particular value, but only that it lies between two values, and that's the subtle distinction. So I'm going to underline that, because if I want to find the probability that we are exactly 3, well, continuous, we cannot include the 3, so we say 2.5 to 3.5. So if we wish to calculate the probability of exactly 3, as I just said, we would find the probability between 2.5 and 3.5 successes, and that interlying part is what we want. So just think back, a couple examples ago, we looked at the distribution of rolls of 6s in 4 attempts. And you'll notice that the binomial distribution is definitely not symmetric. It's got this exponential decay that you would expect from just 4 rolls with 5 options. Now, the probability has a mean and a standard deviation. We said the mean is n times p, or the number of trials times the probability. So we got 2/3, with a standard deviation of the square root of n times p times q, which is 74.54%. That makes perfect sense that the expected number of 6s in 4 attempts would be 2/3, with a standard deviation about 3/4. Like, the logic holds that that's what we would expect to get. Now, suppose we rolled the die 100 times. The table and bar chart would have 100 entries, making it really cumbersome to display. But we could still calculate the mean and standard deviation of the binomial distribution. We do n times p, 100 times 1/6, which is 50/3, or 16.67, and our standard deviation, which is the square root of 100 times 1/6 times 5/6, which is 9.128. Or that's how much we would expect to vary from getting that number of 6s. So we do not have another option for displaying the distribution. We do have another option for displaying the distribution if we meet a couple of conditions. So let's talk about those. Now, to get an idea of the other option we might use to graphically represent the distribution, let's look at a few histograms of building up for the distribution of the number of 6s in 4 rolls. So let's say we did this 10 times, where we rolled it 4 times, we counted the number of 6s. This would be the probability distribution, expected value, and our standard deviation. If we increased it to 15 rolls, this would be the expected value and standard deviation. As you see, the skewedness is starting to kind of rectify. In 20 attempts, we get our mean is 3.3 and our standard deviation is 1.67. If we go to 50 attempts, there is this nice uniform where our model is tending towards being symmetric, even though clearly earlier on it was not. And then finally, if we get to 100 attempts, we get this almost normal symmetric distribution. So if you notice this trend, as the number of attempts n increases, the distribution approaches a unimodal and symmetric distribution. And that's key for us to note. When n gets large, the rectangle's width gets small, we get more of them, it's going to be close to normal. So hopefully you notice the distribution of a binomial becomes very unimodal and symmetric when the number of attempts becomes sufficiently large. If we show the normal curve with a distribution of 100 attempts, you can see it very closely approximates the binomial. As p approaches 0.5 and or as n gets large, the binomial distribution approaches normal. Think back all the way to that Galton board where everything was dropping down. If we expect p to be 0.5 and we see a sufficiently large number of attempts, we should get this normal distribution. When n and p and n and q are greater than or equal to 10, and this is our condition, the normal distribution can be used as an approximation for the binomial distribution. And oftentimes, it's far easier to work with the normal model, with all of the work that we've done with it, than the binomial distribution. So the normal approximation must be used with caution. Our example of four rows and recording a 6, n times p would be 0.67, and n times q is 3.3. We fail on both counts and cannot use the normal approximation to the binomial. So when we fail these conditions, and we always have to check, you always have to check the conditions. We need to make sure that we satisfy the conditions in order to justify using a normal model. So to use the normal approximation, we would need at least 30 trials. So 30 times 1 6 is 5. 30 times 5 6 is 25. Or even better, would be for 60 trials. 60 times 1 6 is 10. 60 times 5 6 is 50. So that's greater than or equal to 10 on both. So there is another problem with the normal approximation to the binomial. Remember, binomial has two discrete results, success and fail. And the number of successes is an integer, also discrete. However, the normal curve is continuous, and that's the trouble. And we're not going to go into the calculus of this, but we must have this correction factor for being continuous as opposed to discrete. So the correction factor is to use an interval to represent the data centered at the value you want. So for example, rolling 1 6 on the die, we use the value 0.5 to 1.5 for the probability of 1. See how we changed the interval, so we covered the range. It's equidistant. 1 is between 0.5 and 1.5, and that is our little caveat. So rolling 3 6s on the die uses the values 2.5 to 3.5. So we want 2.5 to 3.5 would be our value. So that's our continuity correction factor. So again, if we want greater than 1, we want the probability that x is greater than 1.5. That's the closest half-step interval. If we want less than 4, we want to exclude 4, so the next closest would be 3.5. If we want greater than or equal to 4, use less than 4.5. Sorry, less than or equal to 4.5. We want to include that number, so we go a half step over it. If we want to be greater than 4, we just say greater than 4.5, exclude the value. Greater than or equal to 4 would be one step below it, because we want 4 to be in that interval. And then once we have that, we just use our normal model. So the probability that we are less than 4 would be from negative really large number to 3.5 with our mean and standard deviation. And we just do our normal CDF thing that we've constantly used. That is the amazing thing about this approximation, is the work that we practice with the chapter 6 is the same work we're doing here. Think in terms of the interval representing the value of interest. Greater than or less than do not include the number and do not include the interval. Greater than or equal to or less than or equal to do include the number, thus are included in our interval. It's a little work, but it allows us to do some easier calculations.
For a distribution of the number of 6s in 50 rolls, we can use the calculator to find the probability two ways. On our calculator, find the following values using both binomial and normal distribution. So if I want to find the probability of getting less than 7 6s, I could use my calculator and go menu, statistics, distributions, and then I can go binomial CDF, and I have 50 trials. The success is 1/6. Our lower bound is 0. The upper bound is 7. sorry, the upper bound would be 6 because we want up to including that. We hit enter, we get 0.2506. If instead I used the normal model, and you can see statistics, distributions, normal CDF, our lower bound is going to be negative a million. Our upper bound is going to be 6.5. Notice half step below. Our mean, which we found, is 8.3333, and our standard deviation is 2.62. Sorry, 2.6352. Hit enter. And notice these are not quite the same number. And that's why we call this the normal approximation. Likewise, if we wanted to do the probability of x is greater than 12 sixes in 50 rolls, we can either do 1 minus binomial CDF. If you have a TI Inspire, what you're changing is the lower bound to the upper bound, being a really large number. Or we can do normal CDF, but if we're using normal CDF, I just want to note that we are a half step higher because it's our normal approximation. So keep in mind, it's called the normal approximation for a reason. Okay, for a distribution of the number of sixes in 50 rolls, we are using our calculator. So if it's less than or equal to, we can either use binomial CDF, which includes the number, or normal CDF, we want to be one step higher. If we want to be greater than or equal to 12, binomial CDF would be 1 minus that, or 12 and higher. 12 to 50 would be our upper bound. Or we can do normal CDF 11.5 to a really large number. Notice they're approximately the same. And so sometimes it'll be easier, more precise. Sometimes it'll be less precise. In fact, the higher n is, the more the normal model approximates the binomial. So we can now use z-scores to find probabilities of success or fail. So the things that you have to do is 1, make sure you can use the normal approximation. So this is the first check we need to do. NP and NQ are greater than 10. Step 2, we'll find our mean, which is n times p, and our standard deviation, which is n times p times q, square root. Third, we write the probability using the appropriate interval correction factor. So half step up, half step below. We'll find the z-scores for the values of the interval, and then we'll finally find probability. I'm going to make this emphasis yet again, but do not forget, answer the question with a sentence. So for the distribution of number of sixes in 50 rolls, we can use z-scores with the normal approximation to find the probabilities. When calculating z-scores, you got to be certain to use the values determined by the continuity correction factor. Okay, so our binomial CDF, or what is the probability that we get less than 7 sixes in 50 rolls? We would do binomial CDF 50, 16, 6, which is 0.2506. You could also do a z-score, which would be 6.5. That's our correction. That's our mean. That's our standard deviation. And then you could just do normal CDF, -9 to the z-score and 0, 1, hence using that standard normal model. And look, we get approximately the same value. So what have we learned? Bernoulli trials show up in lots of places. Depending on the random variable interest, we might be dealing with a geometric model, up until how many successes, or a binomial. What's the probability we get this number of success, or the normal model? So to keep it straight, geometric model, when we're interested in the number of Bernoulli trials until the next success. Binomial model is when we're interested in the number of successes in a certain number of Bernoulli trials. And then the normal model is to approximate a binomial when we expect at least 10 successes and 10 failures. So let's do an example. A new sales gimmick has 30% of M&Ms covered with speckles. These groovy candies are mixed randomly with normal candies as they are put into the bag for distribution and sale. You buy a really large bag and remove the candies one at a time, looking for the speckles. You want to see what happens. So is this a Bernoulli trial? And yes, we can say that. Either the candy has speckles or it does not. The probability of success is 30% or 0.3, and the number of M&Ms available is so large that removing a few M&Ms does not significantly change the probability of the next selection, thus sufficiently independent. However, if you had one of those small mini bags and you're doing the same thing, this would no longer be true. So the bag has to be sufficiently large to do this. So what's the probability that the first speckled candy that Benjamin King Kong finds is one of the first 3 he selected? Well, that would be, the first probability is just a geometric. This would be geometric, and we have 0.3. If we want, we can do that on our calculator. We're going to get 0.657. So the probability that the first speckled M is in the first 2 candies is 0.657, which is geometric CDF. How many candies do we expect King Kang to pull out before he finds a speckled? Well, the expected value is 1 over P. This is, again, geometric. So 1 over 0.3, which is 10/3, or 3 1/3, he would have to pull before he gets his first speckled. So what's the probability that Mr. Arnaud Bojangles finds 2 speckled ones in a handful of 5 candies? So now this is a binomial. So we use binomial 5, 0.3. And we want to know if he gets exactly 2. So we would do binomial PDF n5 p.3 x is 2. So the probability of getting exactly 2 speckled M&Ms in 5 candies is 0.3087. In a statistics class, students miss class 70% of the class days if this was a normal year. If the class has 38 students, find the probability of no absences on a given day. Then find the probability of 3 absences on a given day. So there's only 2 possible results. Either you're in class or you're absent. Success is absent. Trials are independent. No, there's only 38 trials. So the probability of success is 0.17. It's weird to think absent is success, but okay. So we have a binomial trial. What we're trying to find is what's the probability that there's 0 absent students. So we just go binomial PDF, 38, 0.17, 0. Type that into your calculator, and you get the probability of 0 absences on a given day is 0.0008, or 0.08% of the time. What's the probability we get exactly 3? Again, that's a binomial PDF. What's the probability that x, which is our random variable, or the number of students that are absent on a given day, is 3? Here is what the binomial looks like. If you type it into your calculator, you're going to get 0.0610. So the probability of exactly 3 absences is 6.1%. So what is the expected value of students absent on a given day, and what is the standard deviation for the number of absences? So this is a binomial. So we go to expected value, which is n times p. So 0.17 times 38 is 6.46 absent students, with a standard deviation of square root of n times p times q, which is 2.3156. So let's put that into a sentence for context. The number of absences on a randomly selected day is 6.46 students, with a standard deviation of 2.3156 students. So to ensure you have a complete answer, the following elements must be included in your response. So 1, you need a probability statement. I keep reading over these, but you need to say the probability that we have our random variable equals a number. So whenever you use a variable, be sure to define that variable. What is x? How you calculated the probability? Are we using binomial PDF or CDF or geometric PDF or geometric CDF or normal PDF or normal CDF? Appropriate arguments, and the AP test will most likely ask you to write it with NCR, P to the R, Q to the N minus R. The probability to, I need the probability to 4 decimal places. I need a sentence stating in context your result. And if a normal model is included in any part of your response, all elements of a normal must be included. Mean, standard deviation, probability, what your limit might be, and appropriate labeled drawing of a normal model. We will always be drawing a picture. few little things in case you forgot. If you're on TI 84, if you want to find the factorial button, you hit the math, then you go over to the fourth row, and then you hit 4. To calculate combinations, you go math, PRB for probability, and then you go 3 for NCR. In terms of notation, we write 10, choose 5, or 10, choose 5, which is math, probability, 3, 5, enter. To calculate binomial probabilities, this is in our second vars, or distributions. So binomial PDF, you have NP and X. Binomial CDF, you have NP and X. PDF calculates exactly X successes. Binomial CDF calculates no more than X successes in N trials. So CDF means cumulative, or think adding. If you just do binomial PDF N comma P, that gives you your entire distribution. To calculate geometric probabilities, we go to second vars, or statistics distributions. This calculates the probability of the first success is at exactly X attempts. So P of X is equal to X, with the probability of success P. Geometric CDF, this calculates the probability of the first success is N at most X attempts. Okay, one more example problem to finish this up. A doctor's office claims that it keeps appointments on time 65% of the time. Yeah, sure. If 120 patients are seen in 1 week, what is the probability that at least 65 patients will be seen on time? So we have N, which is 120. We have P, which is 0.65, which means Q, the complement, is 0.35. Of course, we're going to check N times P, where expected value is 78. N times Q, which is 120 times 0.35 is 42. So a normal approximation is appropriate. With our mean being 78, hey, that's pretty nice that it's right there. And our standard deviation is the square root of N times P times Q, or the square root of 120 times 0.65 times 0.35, which is 5.22494. And I just want you to think, if you've got mean and you've got standard deviation, we are creating our normal model. I should see a picture of that. So our mean of 78, 1 standard deviation, which is 68%, 2 standard deviations, which is 95%, and 3 standard deviations, which is 99.7% of our distribution. Just good reminders. So what we are looking for is the probability that at least 65 patients are seen in time. So the probability that X is greater than or equal to 65. So if we are going to use this as a binomial, we would do 1 minus binomial CDF 120, comma 0.65, comma 64. Or we would do binomial CDF 120, 0.65, 65 to 120. And you can do lower bound to upper bound on the TI Inspire, and you will get 0.9951 or 0.9945. If we do our normal CDF, we need our correction factor. Our correction factor is, so we include 65, so we go 64.5 to a stupidly large number. Mean standard deviation, which we get 0.9951. Again, it's an approximation. So the probability of at least 65 patients seen on time is 99.5%. Now, in 2012, 80% of households in Great Britain had an internet connection. Does this qualify as a binomial? There's only 2 outcomes, finite trials. Each home is independent. But is the probability constant? Most likely not. How many homes should we survey if we want to use a normal approximation to find probabilities? So we need NP and NQ to be greater than or equal to 10. We have 0.2 times N is greater than or equal to 10. So N is greater than or equal to 50. We always use, if P is 0.8 and Q is 0.2, we want the lower one to figure out what N is. So we need a sample of at least 50 homes to use a normal approximation. If we were to survey 150 homes, what is the probability that at least 130 homes have internet connection? So again, we write our probability statement. If X is the number of homes that have an internet connection, we want to be greater than or equal to 130. Now, this would be either a binomial CDF or a normal CDF, depending on if we want to do the z-score translation. If we're looking at a z-score, we are also going to find the mean, our standard deviation, and draw a picture with our cut line and shaded above. So the probability of at least 130 homes with internet is about 0.0262. If we were to survey 150 homes, what's the probability that no more than 130? Well, no more than 130 is where X is less than or equal to 130.5. So everything up to that point, and we would see that using our normal model, we would get 0.9840. So the probability of no more than 130 homes with the internet is about 99%. I know I went through these examples at the end pretty quickly, but I want you to get the flavor of what we can do, either the binomial or the normal approximation, to represent these probability models. So that wraps us up for Unit 4. Thank you guys so much for your attention. We will finish this up with some in-class work, and then we will test on Unit 4. See ya.